Well, welcome to us intimate group here at the IDL in Boise, Idaho. On behalf of the University of Idaho Integrated Design Lab and Montana State University Integrated Design Lab, welcome to our fall education series. We have a bunch of events coming up here in the near future. I'm going to shout out really quickly. Obviously, this is the first in our series of 5 presentations with on various topics, kind of a catch bag. We often do themed series here at the lab, and the theme of this series is all the talks that we've wanted to do over the last year, but we couldn't fit in another series. So that's what we're having tonight. Great talk from Abhijeet Pandey at the Heshang Mahon Group, and followed up on October 10th with energy programming from SolarC, which some of you might remember from other presentations in the past, Mike Hatton. And we're having a local group on the 17th of October, Idaho Central Credit Union, and their high-performance building in Pocatello. Skip a couple weeks for Green Build and for Halloween and whatnot, and on November 14th, the low-cost high-performance buildings. We're having a couple of examples of 2 projects in Idaho and getting into the nuts and bolts of, I should say, the dollars and cents of costing issues. And then on November 28th, a presentation on a study of natural ventilation, two summer-long study of natural ventilation in Idaho here. Really quickly, there are some upcoming events from the Lighting Design Lab here in town. There are handouts in the back of all this stuff you can grab. And those are on October 10th, 2 lighting workshops from 10 to noon and from 1 to 3. And then finally, around the Idaho Energy Conference and Energy and Green Build Conference on October 24th through 26th over at the Doubletree Meeting the Sustainability Challenge. And part of that event is the Better Bricks Awards. And that's where we award, kind of honor local professionals doing exceptional work. So I think that's most of the formalities. Registration in the back for CEUs for AIA or for engineering professional credits. I think for the engineering credits we'll get some sort of certificate printed. Actually, it's already printed, so we'll have Abhijeet sign it when you leave today. For folks online, we can coordinate that with you for engineering credits or AIA credits online. Just submit your information and we'll send you a certificate. And I think on behalf of the University of Idaho and the Integrated Design Lab here, welcome to Abhijeet. Thanks for coming up from Sacramento, or Oakland as it is.
Oakland, thank you.
In your case. Abhijeet's going to be talking about daylight sensing electric lighting controls and top lit and side lit applications, what works well and what's not been working so well. So feel free to chime in. It looks like we have an intimate group tonight, so let's make it conversational. And I think Abhijeet will have some good information for us. So you have your lapel, so you don't need this.
I think
Welcome.
so.
Thanks for coming.
Thank you. Thanks, Kevin. Well, if I might give you some theme for this 5 lectures, integrated design, because I'm going to go somewhat into that direction. But that's sort of been the constant theme of a lot of work we've been doing at the Heshang Mahon Group. And these 2 projects that I'm going to talk about are part of that. And before I start talking on this topic, I usually start by giving a little bit of background on myself, and depending on whether I'm talking with architects or engineers, it changes. If I'm talking with architects, hi, I'm an architect by training. If you're an engineer, don't be offended. I now work as an energy efficiency consultant, and I can understand your language, so I can work both languages, so that's good. So what I'm going to talk about today is results from 2 studies that our company did on with funding from various utilities, including the utilities group up here, on what shapes a good daylighting system and what works in the field versus what doesn't. So without much ado, that's the issue. We are all swimming in daylight, and the question is, how can we best bring it in? And seems a simple enough problem because it's all out there, all 10,000-foot candles of it. How do we bring 30 or 50 of these in our buildings? That's the question. Briefly, when we talk daylight, I'm talking about both daylight in terms of light from the sky, the reflected component, as well as the sunlight. And We're going to go in detail about these two because these two affect the daylighting quality in the space very differently. So unfortunately, I'm not old enough to remember these in the US, but where I come from India, and that's still the case, thankfully so. But here, before we had a lot of electric lighting, or before it became sort of standard practice, we used to have daylighting everywhere, and that used to be our daily pattern. We sort of adjusted our activities around the daylight. Then, of course, we got the machines, and then we got all the wonderful things like air conditioning and low-cost construction techniques, and we got ourselves boxes. And when you have those boxes, you can go deeper. You can do without windows, those pesky things that leak and bring in sunlight and all that. And who wants those distractions anyways? A lot of schools actually went away from doing windows, not because they didn't like the sunlight, but because they thought, hey, if the student's going to look outside, he's going to get distracted, so let's erect walls around them. And we apparently do that with our workers too. So, thankfully we got the Dilbert cartoons out of that. And I'm not going to say anything about that, but that's the reality. The point I'm trying to make with this is that we have standards on lighting quality and lighting quantity per se, and those are, we started doing those way back in 50s, and as the point up there is, we didn't get 100% agreement even back then. These are sort of the 80% rule, 80-20 rule. 80% people agree with it, let's go with it. Not everybody is going to agree with everything. The point is, since 80% of the people have agreed that this is the standard, there's going to be some people who are going to require higher than this, but there's going to be awfully lot of people who are going to be happier less than that. So here's sort of a curve. You have your sort of 80% people saying, yeah, I need 50-foot candles in the space, but at least half of them are going to say, no, 20-foot candles is fine. Of course, there's going to be some which are going to be above this range, but the point is, give people the control on their daylighting in their building or the light levels in their building, chances are that they're going to choose something lesser than what this 80% rule says. And this is one of our company principles. The reason we have this photograph up here is this is the same person, and he's happy in both these settings. We don't necessarily need to have that 10,000-foot candles inside our offices to be equally happy in our offices. Agreed that Doug is kind of a Batman. He likes to work in his bat cave and it's dark. I wouldn't work there. But the point is, we all have our preferences, and they are different. So what do I mean by daylighting? I talked about lighting from the sky and light coming in from the sun. But how do we get that in? We get that in either through skylights or through windows. But here's the forgotten piece of daylighting, and that's what I'm going to concentrate on today, is lighting controls. If we have the light coming in from outside, but we leave our electric lights on, we haven't done daylighting. And so I want to really stress that point, and we're going to come back to that later in the presentation of why that's important. So just a brief idea of what the energy savings potential is, and this is, I'm sorry, these are California-specific numbers. The numbers here might vary, but the point is that there are significant savings possible through doing daylighting and by turning off the electric lighting. And we found, for example, that for a retail chain in California, the primary motivation was to save energy. It wasn't any sort of green inherent interests or trying to be sort of one-upmanship that seems to go on now more often. But the point also was that they could have gotten at least 3 times as much savings if they had done it right. So intentions are good. They want to do the right thing. You could do more. Here's sort of another set of numbers. If you're looking at the lighting energy itself in the buildings with proper daylighting and controls, you could save anywhere from 30 to 80% of your electric lighting. As an example, I work in a building. I never use my electric lights at all. I have pretty good daylight. The only time I use it is when I work after 7, which, thanks to being married, I don't do that quite often anymore. But whenever I do, that's the only time I use the electric lights. How much does that convert to whole building energy savings? Depending on what weather you are in, 5 to 50%. And then this is kind of becoming a bigger issue now, is peak electricity use. One of our local utilities in Sacramento has to essentially double its capacity to provide electricity for that 50 hours of the summer when it's 110 degrees or 100 degrees outside and everybody is using their air conditioning. Point is that daylighting can be an excellent strategy to get to those peak savings. If you can just turn off the lights or dim them 20%, you get your 10 to 20% energy savings. And the other point is that it works forever. You get it to work right once, it's going to work, and if it is ever broken, as if the power goes out or something goes wrong, you have made sure that your building has enough light for people to survive and work if need be. I recently did a case study on a fire station and a police station, critical facility, where they used this principle to design their building, not because, again, they wanted to maximize their lead points, but because their whole situation was if California ever has the next blackout, they want to make sure that they at least can work and get all their functions done with their backup generators supplying their basic functions, but they don't waste that on lighting and other things. So what's the secret? I have sort of, and some of these numbers might be changing now, but here's sort of an idea of the efficacy of different light sources that we work on, and these are expressed in terms of lumens per watt. So how much quantity of light would you get if you supply 1 watt of electricity to that particular device? Our good old light bulb is down there, right around 15. Some of our most efficient technologies are trying to get around the 100 lumens per watt. But with daylight, you'll see that the potential is much higher. You can, especially with a clear sky, and if you avoid the direct glare from sunlight, you can have pretty incredible lumens per watt. How do you do that? This is one of the strategies, low E glazing. You have 100 watts per square foot of heat coming in. You have a low solar heat gain coefficient. You get 40% of that inside. The same window can actually let in 70% of the illumination. So when you're talking about the luminous efficacy of this, you're talking about 175 lumens per watt. That's almost twice of any current electric lighting technologies. So here's another example. I was mentioning about why controlling these electric lights are important, because if you're getting that 175 lumens per watt, and yeah, if you can see in this one, we're adding skylights to a building. This is a skylit retail store in Fresno, and down here is the amount of skylights that you add. So that's the percent of floor area that the skylight occupies. And as you can see, as the skylight ratio increases, you get additional savings, and sort of you don't get infinite savings. Once you start getting beyond a certain range, your heating loads increase, so your net result is more energy consumption, not less. But the point is, if this store didn't have any electric lighting controls, daylighting controls, this is what would have happened. You're adding skylight, you're adding this beautiful daylight in the space, people are happy in it, but you're increasing your energy use constantly without turning those lights off. Here's another way to look at it. Again, the same sort of skylight ratio. Now we're looking at the energy savings from skylights. As you increase the amount of skylights in the space, you're increasing the lighting savings, but again, they sort of taper off after a certain limit. You get some cooling energy savings because you're reducing the amount of heat the lighting system is putting into the space. You are increasing the heating. Here's what happened with the total energy use. So beyond a certain limit, your total energy use is going to start increasing, your savings start decreasing. Same thing in terms of the energy cost. So the point is, daylight is a great thing, and we all should do it, but too much of a good thing is a bad thing. And we're going to come back to that in the later parts of the presentation. But the point is, we need to be intelligent about how much we use that daylight. And here's the problem. Can we get those promised savings? We have all our energy savings models and simulations that are going to tell us we can save 50% of our building energy, but can we get there if we don't do the design right, or if we don't get those photo controls to work? So that's the challenge. If people start taping over sensors or turning their blinds down and turning the lights on full output, what's the use of these, daylighting apertures? So I'm going to cover two studies, as I said. One of them, the first one we did in 2003, that looked at top-lit buildings. These are buildings with skylights. Second study we did for side lighting. These are buildings with windows in 2005. In each of these, we compared the on-site energy savings against a 2-week sort of calibrated annual energy simulation model. And what we came up with is a realized savings ratio. I'm going to go into that later. But the point with that is we wanted to compare how much energy is being saved on site versus how much our latest and greatest models are saying we could save. Briefly, how many of you are aware of the photo control system and what the components are? And I can skip over this if you all know about this. So looks like we can skip over this. All right. So we got the photo sensor, the controller, and the control device. You can have the sensor looking either down in the space. You can mount it on the fixture. You can mount it outside. You can have a simple on-off control. You can have a multi-level switching control, so you get a little bit more fine-grained details in your lighting control. Or you can do dimming, which is kind of the Cadillac of the daylighting control solutions. Your electric lighting levels will vary directly proportional to the outdoor daylight. The point I'm going to sort of belabor, and I'm going to come back to this, is both if you're doing switching or dimming, there's a thing called as a dead band, not a thing that the control system drops dead in it, but the idea is that for each of these, you need a set point when the lights are going to turn on. So if the daylight is, say, below 20-foot candle out here, the lights come on. And then you need the lights to turn off when the daylight is above a certain limit, say 50-foot candles. The point is, if they are too close, you're going to get cycling and you're going to have lights come on and off or dim up and down. It's a nuisance to the occupants, and it's going to also eventually burn out your lighting system much faster. So the point is, we need to have that dead band, and we need to have a time delay so that it's not just cycling with the outdoor lighting. Obviously, there's various types of photo control equipment, and I'm not going to, again, go in a lot of detail, but you can control things at the individual fixture level. You can control it at the circuit level. You can control it at a whole facility level. And as you go sort of more towards the fixture, the system gets more and more complicated because you have so many more components that you're trying to control independent of each other. You can do lighting controls alone, or you can do them part of the EMS. Here's an example of an EMS system, or you could just go sort of circuit by circuit or with a simple power pack. So what's the best control type, or what's going to give you the most savings? Well, the classic consulting answer is it depends. What's your occupancy type? What are you going to control these lights with? How do you want to control them? What's the quality of light you need in the space? Is this a museum quality lighting? Is this lighting that you require in a storage room? What's your energy savings target? Let's say you're very aggressive and you want to get that 50% savings target. So there's lots of opinions and little evidence, and I'm going to present what evidence we have. Let's start with the top lighting. There's lots of myths about skylighting and skylighting controls in general. They are hard to understand. They are very hard to install. They fail very often. They're going to annoy the occupants, and they're going to, never use them again. The skylights are going to cause too much heat gain, and yes, they're going to leak. So that's sort of all the issues we're going to look at. So what we did was we did this is back in 2003, and this is California specific, but we looked at about 150 buildings that had skylighting and had daylighting controls, and we gave them a call, talked with them about what their systems were, see if the photo control systems were still installed on site, and completed interviews with them and said, can we come to your sites and take a look at this and verify how much they are saving? Of those, about 46 said, yeah, you can come ahead and do your service. So we went there, we did some power metering, did the analysis, and we're going to look at that next. So to look at what types of spaces we did, now remember this is top lighting skylights, so you'll see a lot of buildings which are sort of the large big box buildings. There's manufacturing warehouses, there's retail buildings, a few offices, and a few classrooms. A lot of these, because again they happen to be part of that big box retail chain or manufacturing, the lighting is part of the whole building EMS control system. It's not a standalone, although we do have a lot of buildings that are controlled individually. This last bullet here is kind of interesting, right? We called 160 people. We confirmed with them that they had photo controls. Yeah, we have skylights, we have controls. Come on site, you can verify savings. 3 sites, there weren't any photo controls. One of them had occupancy controls. The other side, they had light switches. So the point is, a lot of people don't know about this. They think they do sometimes they don't. Here's what people told us their systems were doing. Overall, pretty good picture, right? When 46 sites visited, about 36 of them are working or working with very minor problems. Only 2 sites, they told us the photo controls were not working. 4 of the sites, they said, yeah, they're working, but we're not really happy. We want more savings, so we're just turning off our lights. One site where they said, no, we don't like it. We keep our lights on all the time. As I said, 3 sites, well, they didn't have any photo controls. We asked them if there was, wherever they had this sort of dissatisfaction or, gosh, this could work better, we asked them, what was it with? You know, we asked them about the building type. We talked about what kind of a control system it was, whether it was fluorescent lighting that was a problem or HIDs, whether it was particular occupancies, you know, whether it was just bad idea to do this in offices or classrooms. Was it that the control algorithms, whether it was switching or dimming or multi-level switching, was that an issue that they were unhappy with? Most of the answers said, no, it's not specific to any of these. It says most of them dealt with sort of the details. They either come on too soon, they go off too soon, they fluctuate too much, or you know, they're just doing too many things or too few things. And most of these problems seem to be happening from the time the systems were installed. So it wasn't something that they were happy with and then started having problems with. So we went on site and we did a subset of these sites. Now we went on 46 sites, as I said. We installed lighting loggers on all of these, measured the energy use, and we had to drop a few sites either because our loggers failed or they didn't have photo controls, or you know, sometimes these loggers are pretty attractive targets for shoplifters, so some of them walked away. But anyways, we had 32 sites that we could look at, and we categorized them independent of what the people said into fully automated versus those that were working, but people were manually assisting them. We did the energy savings analysis using Calc. I'm going to skip over this, but it's a software that analyzes the daylighting savings potential from skylights. And this is the realized savings ratio that I was mentioning. So that's the ratio of how much savings we measured on site for those 2 weeks versus how much potential savings there are that Calc is telling us there are from these control systems. So if the RSR, as I'm mentioning here, is less than 1, then the system that is working on site is saving less than the optimal. If it's more than 1, then it's working better than the sort of quote-unquote ideal control. Now this is a very heavy slide, so I'm going to take a few minutes on this. But out here, the first column is what people said their systems were doing. In here is how we categorize them based on our data. So these are the numbers, these are people's perceptions. And then here's the realized savings ratio under both categories. These savings ratios are for what people said their systems were doing, and these are the ratios for how we found the systems were in those categories. Interesting thing is 13 sites where they said it was working perfectly, they didn't mess with it. Sure enough, it was working perfectly. 14 sites where they said it was working, but we do manually adjust those. We found that 7 of those sites, they weren't doing much at all. It was fully automated. 7 of them, they were manually assisting. On 2 sites where they said it's not working at all, we actually found that it was working. It's just working very poorly. They didn't realize that they actually had a system that they could make work if they just tweaked the settings. One of them was indeed not working. 2 of the sites where they said we always keep our lights off, sure enough, the lights were always off. And 1 site which was overridden to be always on was always on. The main point here is to look at this ratio here, the mean savings ratio, is close to 1. So it's saying if your system, if they think the system is working well, or it is sort of working with some minor problems, or we find that the system is fully automated, you're getting somewhat less but close to that ideal performance, and they can go over it if they manually assist it. So they can get better performance because they realize that they don't want those light fixtures, although if you look at the lighting levels, the foot candle levels, they probably might need the lights on. But here's the problem right here. When users start doing things because they are unhappy with their systems, they can have very different results. You can have anywhere from a third of the savings to a third more than your savings. And if you are working in the energy efficiency field, if you're doing programs, or if you're doing this over a large population, that's a problem, because you don't know if your population is coming from these people or these people. So as much as possible, we want to try to get systems to be fully automated and working as well they should as they are in this case. So from this study, there was I used the glass half full, half empty. We found the glass was actually 3/4 full for this one. None of these systems has physically failed, as in none of these needed physical replacement because the hardware didn't work. Nobody had taped over photosensors, nobody had clipped the wires, nobody had done any overrides with intention to defeat the system. Most of it was to actually help the system achieve more. And we got pretty close to the ideal realized savings. So that's the good part. But there's still some of those out there in the market. So here's the story. If you don't get the systems to work right, if they're not happy with it, it's never going to be fixed unless you go in and do some commissioning in those systems. As you can see, most of the sites with manual assist and about a third of the sites, even with fully automated systems, they said that we were never happy with these systems. They never did what we thought they should be doing. And as I said, the problems range from either the lights are turning off too soon or too late, or doing too much or too little frequently. Most of the people, even those where the systems are working very well and saving as much as ideal, they don't know how to make these systems work, or how these systems work, or how to change them. A third, even those buildings that were working well, didn't even know where the sensors were. I had to spend some quality time crawling in attics and over roofs and various places trying to find a sensor which looks that size, right? So imagine a 50,000 square foot warehouse, 20-foot high ceiling, trying to look for this all over the place. Point is, if the owners and the building staff doesn't know, there's no chance if it fails, they're going to know how to fix it. And again, if they do not turn off the lights off, if they don't turn the lights off, you're going to increase the lighting energy use. So we came up with a photo controls guidelines document aimed at manufacturers that first time. And we said, how can you make your products better and inform these people of how they should be working? So we gave them some guidance on how to make these products, the packaging, the information provided with the products, and the instructions that they provide to their installers. And basic principle is keep it simple, keep it understandable, and make it adjustable. If it's not adjustable, if it's not simple, or if they can't understand it, it may work now, but the next time something fails, it's not going to work for the rest of its life. So then we presented this in 2004, and the first question I used to get was, well, this is great, but what about side lighting? Because that's really the problem, because top lighting, you talk about warehouses and retail stores, but most of our buildings are like this. We have offices, and so what's going on there? Our hypothesis was that we're not going to find such stellar results for side lighting as we found for top lighting. One, it's a lot difficult process to get lighting into your space through side lighting, especially if you have a deep floor plate. So we did a follow-up study, and this one we did in Oregon, Washington, and California, so it was a little bit more widespread, so we could get more climates and more building types. And we looked at sort of which of these factors would start affecting that photo control's performance and see if it works well or less well than with top lighting. So again, sort of similar idea, find lots of daylit buildings, call them up and say, hey, do you have photo controls? In most cases, explain to them what photo controls are and what they should be doing, and saying, do you have those? Do you have a device that kind of looks like this and is hanging out from your ceiling or something? And then asking their permission and going on site, doing our survey, collecting data, and then analyzing that data to compare to what they were saying. So this time, again, we called about 163 buildings. We asked them if they had photo controls. If they had them, we asked them if they were working, and most of them were saying, oh yeah, we put them in and they work great, yeah. Later on, we found out that they were kind of optimistic in how much their systems were working. But in general, if they were working, if they said it was working, it was indeed working. Or if they said, no, it doesn't work, never worked, it never was working. The second point was important, though, is although they knew if there was a system that was working or not, their estimate of how much energy they are saving was very inaccurate. So you ask somebody on the phone and say, hey, you install a photo control system, how much do you think it's saving you? Oh, 50% or 5% or 2%. And the results may or may not have anything to do with this. The point here is most of them, even those that said my system is not working, were very satisfied with the performance. Go figure, if they have disabled it, I don't know why they are satisfied, but they were satisfied. So here's a typical space, and this is a fisheye picture of this. Why I'm showing this is in side lighting, it's kind of important to establish sort of a critical point in the space where you would say, this is where I'm going to measure the daylight, because close to the window right here, you're always going to get ample light. But if you're back there where Kevin is, and if you're controlling lights where Kevin is my system going to work? So we looked at the spaces and we sort of divided the space into the daylit zone. So all of these, which are controlled by the daylight sensor, are in the control zone. So in this case now, this first row of light fixtures was controlled by the daylighting sensor. So that's our control zone. In each case, the furthest spot in that control zone away from the window was our critical task location. Now, if that happened to be the water cooler, we tried not to do the water cooler, tried to do a workspace. So the idea is that that person who is working there is most likely going to be irritated if the lights are going to be turned off and he or she doesn't have enough daylight from the windows. So we installed loggers looking at daylight coming in from windows. We installed current loggers on electric lights, both the controlled fixtures as well as the uncontrolled. Uncontrolled as in those not controlled by photo controls. They might have other controls like manual switches or occupancy controls. So we could sort of compare those two. We looked at, as I said, the critical task illuminance, and we looked at how much the photosensor was seeing. So we can see if the photosensor location was part of the issue. I'm going to present sort of some of the good data. I had a few slides with bad data, but I thought, you know what, let's go with the good idea. So here's a very aggressive dimming system. The dotted here's sort of a time of day. You got midnight to midnight, and the lights come on at about 6 in the morning. Without daylighting control, they would have probably stayed on all the time. This is what they are doing, because the dimming system is very aggressive, trying to maximize energy savings, trying to maximize the daylight potential. Here's the sort of the illumination coming from windows as recorded by our loggers. As you can see, this is a pretty aggressive system. It saves a lot. This, on the other hand, is another dimming system which is not quite as aggressive, but it's still saving energy. If you can sort of, it might be hard to see, but these valleys and peaks of the window illuminance sort of correspond inversely with the valleys and peaks in the light level. So this is a good, well-working dimming system which is working in relation with how much the daylight is coming into the space. Here's another way to look at it. Here's illuminance at the window coming in. Here's the illuminance at your task. So let's say that's Kevin's desk over there. and let's say there was no daylighting control, you would see a curve which kind of looked like that. When there is no daylight at the window, there is no daylight at that desk. And as you get more and more daylight, you get that curve. You add on electric light, and you're going to see that when there is no daylight, you have whatever the electric lighting system is set to do. If this was not working, you would see a parallel line going up here, always providing that additional 20, 25 foot candles. But since this is a good dimming system, it's trying to maintain that illuminance level, and it's actually, this is an overly aggressive system. As you can see, it's trying to maintain this level of illumination and actually doing a little bit more. People are just happy with that. They are trying to be more aggressive. So the point is, where they're saving really well. So we went on site, as I said, we asked these people about these systems and said, what do you mean by working well? Or, oh yeah, they put those systems in, and they put them in and it works. So we asked them specifically saying, did you ever commission these things? Did somebody do a full commissioning of these? And it was kind of a fuzzy concept. Most of the people, if they ever had records, they couldn't show us. A lot of cases, commissioning to them meant that the architect or the lighting designer had given them a sheet that said, or a spec sheet from the manufacturer that said, here's what your control system looks like, with a picture of the controller on it. But the point was that even though those systems that I showed here were working very well, none of them could actually show us how they were supposed to be working. Because ideally, we would have compared what that was doing versus what the design intent was. Never was documented. We asked them about complaints. We didn't want all success stories. We were actually looking for modes of failure. So we asked them what their complaints were, and they were sort of across the board. They went from sort of being too hard to calibrate, which sort of was the sort of most common complaint, and then sort of all over the place. We asked them how they were working, and then we diagnosed them, as with the top lighting study, of what the systems were doing on site. And we identified of the 64 spaces that we visited that had no savings, that about half of those they had consciously disabled. They had either adjusted the set points so that the system never works, as in the lights never turn off. They had just overridden the system so that the lighting control panel or whatever device it was bypassed. They had taped over the sensors. They have cut wires. In other cases, about 23% of those, they don't know. Things was installed, but they never worked. They don't know why, either because it was installed, never worked, or they never was installed or not commissioned. In few spaces, they commissioned this thing, it was working, then they decided that there was too much sunlight, closed the blinds, turned the lights on. And about 22%, they just couldn't know. So what was characteristics of some of these spaces that failed? We found out that spaces that had, in terms of daylighting quality, spaces that had only light coming in from one side tended to fail more often than spaces that had daylighting coming from both sides. If there were windows oriented anywhere but north, and this is especially true if they don't have any shading on them, if there was direct light coming into the workspaces, so if there's direct sunlight penetration, or if they have partitions. So, if I have a 6-foot partition right here, there's just no way my daylighting control system is going to work. We also looked at if there were any issues with the people in the space in terms of ownership. We found that often when there were multiple people deciding on what the light levels should be or how those should operate, things tend to be overridden more often. Then it becomes a question of maximum complaint mode. If the buildings were larger, which sort of implies that the systems were more complex, they tended to fail more. Or if the site staff didn't know how the systems were supposed to work, they tend to fail more. In terms of control options, we found that surprisingly switching controls tended to fail more often than dimming. You would sort of think that dimming systems are harder to commission, they are harder to install, harder to understand, that they would fail more often, but we found switching failed more often. But that's only half of the story. I'm going to go into that next. We also found, I talked about large buildings, right? But surprisingly, if within those buildings, whether it were large or small, if the space that you're trying to control with daylighting was smaller, they tended to fail more often. Classrooms worked really well, but everything else tended to work a little less. Offices particularly didn't work as well. And it could be a combination of larger buildings, multiple decision makers, or that you have individual small offices, all sort of contributing to that. As I was mentioning, if you're doing daylighting and if you do this, there's very little potential for doing any daylighting controls. As I mentioned, this is sort of the high-tech duct tape now. You can get it in 50, 60, 75, and 95% transmittance. So 3M is doing a good job on those. I showed the energy savings numbers for the top lighting study. This is similar numbers for the side lighting study. And again, I apologize, sort of these are dense numbers. But the point is, if the systems are working really well, they can save on an average about 1.1 kilowatt hours per square foot. Which, if you look at sort of whole building level, we estimate in California that we can save 4.7 kilowatt hours per square foot by doing the whole building. So by doing HVAC and ventilation and various other things, we can get as high as 4.7. Of those, you can get up to 1.1 with these controls. But here's the kicker. We found that half the spaces we visited had working photo controls. Of the half that had working photo controls, only about half of those saved at least half of what the predicted energy savings would be. So contrast that with the top lighting study, 98% savings compared to the ideal, whereas here you're looking at about 25% savings compared to the ideal. So there's a lot of potential to improve there. There is a lot of potential to get energy savings, but there's a lot of challenges to get to that level. So I talked about things that didn't work. Some of the things that did work though. Older systems tended to work more. Maybe just that they worked and therefore they remained. And newer systems or other systems that didn't work got taken out. Photosensors closer to the windows, the system tended to work better, sort of obvious because you have more direct correlation between daylight and what the control system is sensing. Greater effective window aperture, and I'm going to go into that in the next slide. But the idea is that the better the daylight aperture is, the effective opening into your space that daylight has to come into your building, the better the system is going to work. If those pesky blinds and curtains weren't there in the buildings, things worked great. Smaller buildings tended to work better, either because people were more actively involved or there was one person running the building. Here's the other part, kind of goes hand in hand with the window aperture, is that the control zone depth. I talked about the critical task. So let's say the critical task was out here. That's the control depth. And the ratio of this depth to the height of that window matters a lot. The often used adage for daylighting is 15 foot from windows, right? Doesn't matter if your windows are 25 foot tall or 5 foot tall. We found that actually is not the right metric to use. The better metric to use is this control zone depth to the window head height ratio, because daylighting is geometric. It doesn't do magic curves through your space. So
Abhijeet, is there some guidance later about what those zones, geometries would be?
Yeah, absolutely. Again, as I mentioned, previously I had mentioned that switching systems tended to fail more often, but when they worked, they saved a lot of energy. And both these together sort of are contradictory, sort of, but they make sense. If they are working, if you're turning off all the lights, 100% savings, right? More savings. But if the lights are going on and off too many times, somebody here is going to get annoyed and say, make that stop. I want those lights on. so they're going to disable the system. So switching is more aggressive savings and would give you more savings, but dimming systems tended to sort of last longer if they got them to work well. We also found that this is specifically sort of in office type buildings. If the sensors were not looking down into the space, they tended to work better. Now, that sort of again goes contrary to sort of the what everybody is used to doing, or what everybody is assumed to be doing is put the photo control sort of in the middle of the space, make it look down so it sees both the electric light and daylight. We found that when the photo sensors were actually closer to the windows, looking directly out, tended to work better. As I said, spaces other than offices and classrooms had higher energy savings. Now, classrooms worked more often, but they saved less. So again, the point I'm trying to make in both with switching and with the classrooms is that you can achieve one of the two. You can have sustained savings, or you can have very high savings in a few sites. You can't be overly aggressive on everything. If there was more window area for that given control zone, you had higher savings. You had any remote management of your photo control system. So if the manufacturer is involved, or if there's a third-party vendor that is responsible for maintaining the system and looking over and seeing if it is actually working, chances are it's going to work and save more energy. That's sort of a summary of all the things we talked about. We talked about higher effective window aperture, higher the windows in the space, more systems will save and more it would work. Shallower the control zone, the more it's going to work. Photo sensors closer to the windows and oriented towards the windows, it's going to work better. And switching will save more than dimming, but dimming is more sustained. And the more capabilities you build into your control system to change it, the more it's going to keep working. So coming back to the window, effective window aperture.
Quick question, were there, in your study of the side lighting, did you have any that were combo, top and side, or did you exclude
we excluded those. Okay. Both in the top lighting study and the side lighting study, we had a couple of buildings which were combos. We eliminated those just because we didn't want the results to be sort of affected. So with the daylight aperture, as I was saying, the effective window aperture is a combination of the area of the window, the amount of light that comes in, which is the visible transmittance of the glass, and also importantly, the visible transmittance of the blinds. Very often we don't take the blinds into consideration when we are looking at daylight levels in the space. It's important to do that. So the ratio of sort of a product of those three gives you the total amount of daylight coming into the space. That divided by the control lighting area is your effective aperture. The point is you want to maximize this, and as these numbers indicate, you can do it, essentially 4 different ways: larger windows, more visible transmittance of the windows, more transmissive blinds, or lower controlled area. You can do any of those 4 to get your higher effective window aperture. Similar results, these are again tied into, as I said, the ratio of the window area to the controlled area. We already covered this, dimming versus switching. So here's coming back to your question, Kevin. So what we did was we looked at the energy savings for these buildings where things were working really well or not working at all. So in this graph here, RSR is the realized savings ratio, which is on-site savings versus predicted savings. So if the RSR is 0, it means that the system is not working on-site. RSR greater than 0 means the system is working, but it's not optimal. If RSR is greater than 0.5, you are beginning to come to sort of close to optimal. And the key graph here is we're looking at the control zone depth to the head height ratio. So again, what's the distance of this critical task from that window as compared to the height of that window? And what we found was that we had ratios as high as close to 5. So imagine a 10-foot high window. They were trying to control lights 50 foot deep. Doesn't take a lot of thinking to think that that's not going to work. Things that did work really well were those where the maximum ratio didn't exceed 2. So if it's a 10-foot high window, you can go up to 20 feet. Now, why that's important is the old adage of 15 feet is that with this newer ratio, you actually increase your potential for daylighting. Used to be that you would concentrate only on the 15-foot close to the window. But if you have a library with a window 20 foot high, why not go beyond the first 15 feet? And what it shows is that as long as you maintain that ratio, you can get energy savings that you expect. You don't have to just limit yourself to the first 15 feet. As I said, the age of the controls surprised us because the older systems tended to work better than the newer ones. Sort of indicates that the controls technology itself had not much to do with the operation of the control system. That if they work, they continue to work, or if something is new and it's not going to work, it's not going to work. So there was no report of equipment sort of failing by itself. It's like, well, I don't know what happened. We installed it, but it suddenly stopped working March of 2006. It's either it never worked or it's working. Some of the examples, as I said, libraries tended to have pretty high energy savings. Going back to my effective aperture and the window head height, taller windows, you can get more daylight further back into the space, you can get more savings. They are owner operated, so there's one person who decides what the lighting should do, easier to get that lighting control. Classrooms which were bilaterally lit, which had windows on both sides, had better energy savings because there was sort of more uniform lighting in the space, and if the teacher is sitting on one side versus the students are sitting on the other side, they both get enough daylight. So most cases the teacher has the control, right? You don't have the students have the control. And so in most cases, if you have more uniformity in the space, the one person who's controlling the lights is likely controlling it appropriately for everybody else, so you get more savings. So here's sort of the summary. Top lighting, great results, worked as well as we thought it should work. Savings potential of 1.5 kilowatt hours per square foot. Side lighting, if they do work very well, they can get close to that 1.1 kilowatt hours per square foot. The top right is the problem. They're only working half the time. They're only saving half of what is predicted where they work. And the only good news is once you get to that 25% population that works, that continues to work. So things are not mysteriously failing one year or suddenly working again the next year. Last couple of slides. Go ahead.
Sorry. On the last slide there, where you said they're only working half the time, and when they are working, they're only saving half the energy predicted. What tools did you use to predict the savings?
Right. We use DOE2 to do that, eQuest in particular. And there's a little bit of concern with that, especially with sort of larger spaces or sort of deeper zones, because some of these tools tend to overpredict the savings from sort of side lighting. And that actually was one of the reasons why we kept that the max RSR that we talked about for working, we kept it above 0.5. So we gave the on-site performance some slack. Whereas ideally we would have looked at only those where the RSR was close to 1, but knowing that our comparison tool was going to overpredict the savings, we gave it some slack. So some of the sort of do's and don'ts for designers in this case. The first one you necessarily can't control, but it might help if you know it, and you can guide them accordingly. If the space is owner occupied and if there is somebody dedicated to maintaining the systems, chances are everything, including the lighting system, would work well. Try to avoid high partitions in the spaces. Low partitions are okay. I mean, you can't avoid partitions, but try not to have 6-foot high partitions, especially not 3 feet away from the windows. Try not to have too low ceilings. Try not to have too many small spaces that you're trying to control when you're doing daylighting control. One, it's just costly. It costs some money to put those controls and sensors in, and it's not cost effective if you have to do 100 of these for your building than to do 10 for 10 larger spaces. In terms of what designers can control, try to maximize the daylight uniformity in the space. I talked about bi-level, sort of bilateral daylighting working better. Higher windows tend to work better, or skylighting seems to work better. Make sure that the photo controller is seeing a lot of daylight. Try to match your control zones to daylight, so you're not trying to control something back there when the daylight is coming in from up this side. And the last two are the most important, frankly, because that's the two which are most often ignored, is make sure that they are installed properly, that they are commissioned. And most of these systems out of the box, they are never told how they should be installed. So somebody with the knowledge of how this system should work should be put in charge of commissioning these systems and making sure that you actually are indeed working. Contact the manufacturer and make sure that you understand what that equipment is trying to do and make sure that it does work like that. And last but most important, train the occupants and provide them with some documentation of how this thing is supposed to work. Daylighting controls are still new. Most people don't know them. And if somebody doesn't know what this thing is supposed to do, chances are they're going to use it incorrectly, or the first chance they get, they're going to install something else that they are happy with, which is a light switch. Don't do these. I talked about doing 2 large control zones. Don't try to be over ambitious and trying to go too deep in the space. Don't try to control your entire flow plate with just side lighting. Limit yourself to that ratio of 2 of the window head height to the control zone depth. Don't do high partitions, as I said. Also, don't do very small control zones. Don't try to do the light fixtures just by the window. One, it's just costly to do that. You're not going to get much savings out of it. And then I came back to that issue of the deadband. Make sure that your equipment that you're installing gives you all the necessary settings like the deadband and the time delay, so that your lighting system is not flickering on and off or dimming up and down if there's a cloud happens to go by. Make sure that the sensor is oriented right and it's looking at the daylight source, that it's not looking at a dark space or it's too far away from the window. And the last two would sort of seem obvious, but most people seem to have a hard time getting those right, is make sure those wires are connected. We went to a couple of sites where they just didn't know why the systems weren't working. So I had to crawl into the ceiling and realize, well, what's this wire hanging loose? Oh, the sensors never connected to the controller, I see. Or they were never controlled, or they were controlling the wrong circuit. Doesn't help if you connect that wire but connect it to the wrong place. And the last, as I said, don't leave them in the dark. Tell them how it should work and how they should change it if they're not happy with it. That's the key, is to give them the ability to change it. And lastly, as I said, commissioning. This is a great opportunity for any would-be commissioning agents to understand how these systems are supposed to work. There's a lot of business out there to make these systems work. Where you can get copies of these studies, you can either go to the California Utilities Codes and Standards group. It's www.calcodesgroup.com, and you can search for photo control under their projects list. We're also coming up with a revised photo controls guidelines aimed at designers this time. The previous one were for manufacturers. This time it's going to be aimed at designers and their contractors. Hopefully by end of this year, early next year, we should have this up on the Energy Design Resources website. And that's it. Oops. Thank you. Any questions?
Thank you, Abhijeet. Yeah, anybody have questions, feel free before we decide to cut our signal, and then we can continue and talk with Abhijeet if we want to.
Mm-hmm.
Anybody have questions? All right, well, let's wrap it up formally, and then if people want to ask Abhijeet questions individually, you can feel free. You're not running away anywhere tonight, are you?
Well, I'm actually driving out to Twin Falls. But
oh, yes. Okay, so you have a drive ahead of you, but
I can hang around.
Good. So look forward to seeing you next week. We have Mike Hatton with SolarC coming in to talk about energy programming, which is an interesting concept for very early in design stages to think about use types in our buildings and how we can be more creative with our use types and our occupancy schedules, especially, and then also how those things interface with equipment and whatnot later, but to take advantage of big block type building moves to think about our space types and our occupancy schedules for energy savings. And also next week, Wednesday, during the day, not in the evening, is the lighting design lab 2 workshops. There's still a few seats available for that. You need to register with the lighting design lab for those 2 particular talks. So if you haven't done so, please do, assuming you want to go. And I think that's it. So Abhijeet, really informative, very interesting. I think a little scary, but I think presented very well so that we can see that there's potential and it's not just all gloom and doom with side lighting and daylighting photo controls for side lighting applications. So thank you for giving us some good direction with what we might do in design stages and installation and use to make it work a little better. So thank you all. Signing out.
Thank you.